This next question is a bit more advanced as it requires us to find the ideal radius for the minimum surface area needed to hold 5,000 meters cubed of a fluid. We know that the volume of a cylinder equals pi r squared multiplied by h, the height, which equals 5,000 meters cubed, and the surface area, which equals 2 pi r squared plus 2 pi r h. Rearranging the first equation gives h equals 5,000 over pi r squared. Substituting this for h in the surface area equation gives 2 pi r squared plus 2 pi r multiplied by 5,000 over pi r squared. This simplifies into 2 pi r squared plus 10,000 over r, which can be rearranged into 2 pi r squared plus 10,000 times r to the negative 1. Finding the derivative of this surface area, we get 4 pi r take away 10,000 r to the power of negative 2, which equals 4 pi r take away 10,000 over r squared, which also equals 4 pi r cubed take away 10,000 all over r squared. We then set this equal to 0, which we can simplify into 4 pi r cubed take away 10,000 into 4 pi r cubed equals 10,000 to r cubed equals 2,500 over pi, which simplifies into r equals the cube root of 2,500 over pi. This answer may not be as neat as the last one, but that does not matter. We can then use this answer to find the height and the surface area of the cylinder. We need to figure out whether the answer is at a local minimum or a local maximum. I'll show you how to find that in the next couple of slides. I also wanted to mention, as well as you being able to use differentiation to find the gradient at a certain point on the graph, you can also find the gradient of a line normal to that point on the graph. By normal, I mean perpendicular to that point on the graph, and you can find it by finding the negative reciprocal of the gradient, as you can see here. We will now be talking about second derivatives, which is simply the derivative of a derivative, so finding the rate of change of the gradient. To help you understand, I need to say the relationship between distance, velocity, and acceleration, because velocity is actually the derivative of distance, and acceleration is the derivative of velocity. This is because velocity is the rate of change of distance, while acceleration is the rate of change of velocity, which makes acceleration the second derivative of distance. Here we have a cubic equation of f of x equals x cubed take away 3x squared plus 5, which differentiates into 3x squared take away 6x, which then also differentiates into 6x take away 6, meaning that the second derivative of this first equation equals 6x take away 6. We can use the second derivative to see whether we are at a local minimum or local maximum. If the second derivative is less than 0, then the point is at a local maximum. You can see this as the curve seems to curve downwards, whilst if the second derivative is greater than 0, it is a local minimum as the curve seems to curve upwards. This was useful for the surface area equation, so you know that you're not getting the local maximum, but instead you're getting the local minimum one when you set the derivative to 0. The point of inflection is when the second derivative equals 0. Before we move on, I want to talk about stationary points. Stationary points is when the derivative equals 0 at that point. There are three main stationary points. Firstly, the minimum point where the first derivative equals 0, but the second is greater than 0. The maximum point where the first derivative equals 0 and the second one is less than 0. And then the stationary inflection point where both the first and second derivative equals 0. But a regular inflection point can have a first derivative greater than or less than 0. Now I want to move on to something different called integration. From physics, we know on a velocity time graph, the area under the curve equals the distance traveled. And since velocity is a derivative of distance, in order to find distance, we would need to somehow find the antiderivative of velocity. This is what integration does, specifically definite integration. It finds the area under the curve, or the net change in area. So integration can be thought of as the opposite of differentiation. To understand how this works, I need you to imagine a rectangle. Starting at one rectangle, we can try and use it to estimate the area under the graph. But as you can see, it is not very accurate. But if we use two rectangles, the estimate of the area is slightly more accurate. And if we use 5, it's even more accurate. And to 30, even more accurate. And then to infinity, where it is the most accurate possible, and so the closest to the real area under the curve. So it is best to think of integration as infinitely many of infinitely thin rectangles under the curve. And it does not matter where the rectangle intersects the curve, as when it is that thin, the difference will be negligible.